Symposium of Physics. We ask all participants to keep their microphone off during the entire session to avoid interruptions. For our Zoom audience, in case of any inconvenience that may arise during the session, we ask you that you send a direct message to the staff who have the name Implexis staff in this session. If you would like to ask Professor Legget a question, please send it as a direct message to Implexis Q&A. For those of you who are attending in person at the Congress Center, you can send your questions to him through our staff. Today, we are joined by Anthony Legget. Sir Anthony Legget, the John D. and Catherine T. MacArthur Professor and Center for Advanced Study Professor of Physics, has been faculty member at Illinois since 1983. He's widely recognized as a world leader in the theory of low temperature physics, and his pioneer work on superfluidity was recognized by the 2003 Nobel Prize in Physics. He's a member of the National Academy of Sciences, the American Philosophical Society, the American Academy of Arts and Sciences, the Russian Academy of Sciences, and is a fellow of the Royal Society of the United Kingdom, the American Physical Society, and the American Institute of Physics. He is an honorary fellow of the Institute of Physics of the United Kingdom. He was also knighted by Queen Elizabeth II in 2004 for services to physics. Professor Legget has shaped the theoretical understanding of normal and superfluid helium liquids and other strongly coupled superfluids. He set directions for research in the quantum physics of macroscopic distributive systems and the use of condensed systems to test the foundations of quantum mechanics. His research interests lie mainly within the fields of theoretical condensed matter physics and the foundations of quantum mechanics. He has been particularly interested in the possibility of using special condensed matter systems, such as Josephson's devices, to test the validity of the extrapolation of the quantum formalism to the macroscopic level. This interest has led to a considerable amount of technical work on the application of quantum mechanics to collective variables, and in particular on ways of incorporating dissipation into calculations. He's also interested in the theory of superfluid liquid through helium, especially under extreme non-equilibrium conditions, in high temperature superconductivity, in the low temperature properties of glasses, and in topological quantum computing. Welcome, Professor Legget.
Thank you. I'll start. Good evening. In 1964, there appeared a little article on physics. It appeared in a very obscure journal, so obscure that it went out of business within a year. It was on a very obscure subject, and the author, although he was quite well known in his particular field, was not at all a household name. At first, this little paper, which is only 5 pages long, drew almost no attention. Gradually, people realized that it was one of the most important papers in physics of the 20th century. And by now, it has actually given rise to the field of quantum information, which is perhaps the most exciting area of current physics, and is the basis of a business which is now worth several $billions. The paper in question was by John Stuart Bell, and it basically proved Bell's theorem. What I'm going to talk about in this talk is Bell's theorem and its implications. So I'm going to start off with some very elementary considerations on classical electromagnetism and photons. I'll then discuss Bell's theorem. I'll go on to the general notion of entanglement. I'll talk about some applications of the idea of entanglement, and if time allows, I will just say a few words about my own special interests in this field, which has to do with so-called superconducting qubits. Next slide, please. Next slide, please. Thank you. So let's first just say a few words about some very elementary considerations in classical electromagnetism. Suppose I have a classical light wave which is propagating into the screen. Then the electric field may be represented by the first line on this slide. That is, it is proportional to a vector in the x direction up the board. But alternatively, the electric field could be in the horizontal direction, transversely. But we can also put together these two fields with different weights and get what is called a classical superposition. That is, an electric field which is the sum of an electric field in the vertical direction and one in the horizontal direction. And that's what's indicated in the little figure there. That electric field would be formally represented by the line which says also solution. It's also interesting that the quantities E sub x and E sub y, that is the amplitudes of the vertical and horizontal fields, may actually be complex. For example, we could have this field which is constant times x plus iy times a time and space dependent factor. And what that actually represents is this. It's an electric field which, if I stand at a particular point in space, the electric field will rotate as a function of time. And that, what's interesting is that an electric field like that, with a complex amplitude, it actually carries a finite angular momentum, and that will be important later. Now, one of the things we can do with a classical electric field is to subject it to what we call a polarizer, which is a birefringent crystal. A birefringent crystal has one axis, for example, the vertical axis, such that if the electric field is polarized along that axis in the x direction, then it will be transmitted. On the other hand, if the electric field is polarized in the horizontal direction along y, it will be reflected. But now what happens if we actually shine on this polarizer a field which is in an arbitrary direction, as indicated by the blue arrow in this diagram, at an angle theta to the x-axis? What then happens, as many of you will know, is that the x component of the field, that's E sub x, gets transmitted, whereas the y component gets reflected. So the transmitted amplitude then, so is the x component, it's the total field times the cosine of the angle theta. Now the energy is proportional to the square of the electric field, and therefore the electric field, the energy which is transmitted, is E squared times cosine squared of theta. The initial energy, which the wave had as it came up to the polarizer, that was just totally squared. So what that means is that the fraction of energy transmitted is cosine squared of theta. And that's what's called Mavis's law. And I hope that's familiar, at least to many of you. Next slide, please. Now, that's classical physics. What happens in quantum mechanics? Well, in quantum mechanics, electromagnetic energy comes in bunches. And those bunches are called photons. And they have what is called a quantum mechanical amplitude. And you can think of that amplitude as corresponding to the classical field amplitude. There's a very close correspondence between those two things. In particular, suppose that a quantum mechanical amplitude psi sub 1 is allowed and psi sub 2 is also allowed, then so is the superposition. That is, I just take psi 1 and multiply it by some quantity alpha, take psi 2, multiply it by some quantity beta, and put them together. For example, suppose that psi sub 1 corresponds to a single photon polarized along the x-axis vertically. And psi sub 2 corresponds to a single photon polarized along the y-axis horizontally. Then if I put them together with the coefficients cosine theta and sine theta, I get a photon, a single photon still, which has a linear polarization at an angle theta in the xy plane. That corresponds pretty closely to what happened in the classical case. Again, just as we had circularly polarized photons, or circularly polarized classical electromagnetic radiation, so we can have classically circularly polarized photons. That's the line with the two black circles against it. And what that formula, what that form of the quantum mechanical amplitude describes is a photon with right or left circular polarization. What's interesting is that the angular momentum carried by such a photon is exactly either plus or minus h bar. H bar, as usual, is Planck's constant divided by 2 pi. That's interesting because, of course, h bar is a very fundamental object in quantum mechanics. Now, what happens if a single photon is incident on a birefringent crystal, that is a polarizer, as we saw in the last slide? Well, if the quantum mechanical amplitude is simply along the x-axis, the vertical axis, the photon will be completely transmitted. If the amplitude is along the y-axis, it'll be totally reflected. Well, so far so good. The photon has still stayed as a single bunch. But now what happens if, in fact, the amplitude is neither of those things, but it's rather the some amplitude cos theta times x plus sine theta times y. In other words, it corresponds to a single photon which is polarized in that oblique direction. Well, now we have a problem because, at least at the level of discussion that I'm doing now, a single photon can't be split. It has to stay as a single bunch of energy. So what's going to happen? Next slide, please. Next slide, please. Thank you. I think, sorry, no, you skipped one, I think. One back, please. So you missed a slide. Could we? Sorry, just go back. Yes, good. Yes, so if a single photon with an oblique polarization, like the blue arrow in this diagram, falls on a polarizer, a birefringent crystal, it really only has two choices. It must be either totally transmitted or totally reflected. So how does the photon cope with this situation? Well, it turns out that it will be either totally transmitted or totally reflected. And the probability of transmission is simply proportional is equal to the cosine squared of theta. And that, of course, means that if I have a lot of photons, the number of the fraction of photons which are transmitted, and therefore the total fraction of the energy which is transmitted, is proportional to cosine squared theta. That's basically the quantum version of the classical Melis's law. Now, the question was raised at a very early stage in the development of the theory of quantum mechanics, can a classical probabilistic theory explain this? And actually the answer is yes. And the way it explains it is really quite simple. Suppose that a given photon has a nominal polarization, which is described by the blue arrow. Then we assume that, in fact, it has a true polarization, which may be somewhere around this blue arrow, but is not necessarily equal to it. In other words, we have a random distribution of the true or hidden polarization variable. And now, when that photon comes up to a polarizer, there's actually a rather serious typo which I've just noticed here. In the next line, it says if the blue arrow is closer to red, it should be if the black arrow, that is the true. If the true polarization is closer to the transmission direction, the photon will be transmitted. If the true polarization is closer to the green arrow, it'll be reflected. And then if it is transmitted, we have to redistribute the hidden variables. But it turns out that with a suitable choice of distribution, the random distribution, we can actually reproduce this quantum version of Malice's law. So there's nothing very intrinsically quantum mechanical about this. It could be explained by a classical probabilistic theory. So at this point, things don't seem terribly surprising. Next slide, please. Thank you. Let's imagine a slightly more complicated situation now. Imagine that we've somehow excited a set of atoms from the ground state, their lowest state, into an excited state. And suppose that the atom can return to its original state, the ground state, by emitting not one, but two photons. And let's just suppose, for the sake of argument, that they're emitted in opposite directions, back to back. They don't have to be, but let's just focus on that possibility. So the atom then drops down from its excited state, that's 0 plus at the top of the board. I'll explain the plus later. It drops down from there to the intermediate level, emitting a photon off to the left. And then it drops from the intermediate level to the bottom level, emitting a second photon to the right. And we'll suppose that the angular momentum of the atom is 0 in both the excited state, the initial state, and the final state. So what now, the question arises, what is the polarization state of the photons? Now you remember that the photon polarization, which technically is written x plus or minus iy, that corresponds to a photon angular momentum, either clockwise in the direction of motion or anti-clockwise. And the actual magnitude of the angular momentum is h bar. Now, it's a general principle of quantum mechanics that if a process can happen either of two ways, and we don't know and can't know which way it happened, we must add the amplitudes involved. So that's perhaps a slightly subtle point, which I'll have to just ask you to take. If you're not familiar with that point, I have to ask you to take that on trust, but it is very important. In this case, we know that the total angular momentum of the two photons must be 0. Why? Well, because the atom started off with 0 angular momentum and ended up with 0 angular momentum. So the photons could not have carried away any total angular momentum. However, we don't know how that was distributed. Was it photon 1, which carried off plus h bar, and photon 2, which carried off minus h bar? Well, that would be the case if the intermediate atomic state had angular momentum n is -1, or is it vice versa? Well, unless we inspect the intermediate state of the atom, which is very difficult to do, we don't know. And therefore, we must write the state of the photons as a superposition of those two possibilities. In other words, we must add the amplitudes for photon 1 to have angular momentum +1 and photon 2 -1, and the amplitude for it to be the other way around. Photon 1 has -1 and photon 2 +1. We must add those amplitudes with a so-called phase factor. And that is actually rather crucial. And that's where the plus comes in the atomic states that I've labeled. Because it turns out that that plus, technically, for those of you who know about this sort of thing, that plus is the parity of the atomic state, and that determines the phase factor. And since the parity is plus in both the initial and the final state, that then implies that the phase factor is +1. Again, I have to ask you for the moment just to take that on trust. So the final result is that the phase factor, the wave function of my two photons is given by the first blue quantity plus the second one. And if we just rearrange that a little, we can actually, with just a trivial bit of algebra, we see that that corresponds to two terms. In the first term, both photon 1 and photon 2 are polarized along the x-axis, and in the second term, both of them are polarized along the y-axis. The 1 over root 2 is just a matter of normalization, which is the technicality. Next slide, please. Okay, so this is just repeating. If two photons are emitted back to back in this particular kind of atomic transition, then the wave function of the photons is that first line. So what does that mean? It means that if photon 1 is measured to have a polarization along the x-axis, then so is photon 2. Whereas if photon 1 is measured to have a polarization along the y-axis, again, then so does photon 2. The two photons must have the same polarization. However, there's something funny about this. The state is actually rotationally invariant, so that I can rewrite this state in terms of new axes in, say, the 45-degree and 135-degree directions, the new x prime and y prime arrows. And lo and behold, the wave function looks just the same in these new coordinates. So now, if one is measured to have polarization x prime, then so will 2. If one is measured to have polarization y prime, then so will 2. That's very characteristic of a quantum superposition. If I had just a classical mixture of the two possibilities, that is, if it was always true that for each individual photon, individual atomic decay, either photon 1 had x polarization and 2 had x also, or they both had y polarization, then it would not transform in that way, and it would look different when you rotate the axes. So that's something very characteristic of this funny kind of quantum superposition. Now, let's ask the question, what happens if photon 1 is incident on a polarizer with transmission axis A, and photon 2 is now incident on a polarizer with a differently oriented, this should be, sorry, transmission axis B? Well, as we've seen, we can choose our axes in an arbitrary way. So let's just choose our x-axis to be A, along A. Then the probability that photon number 1 is transmitted through its polarizer is just the weight of the XX possibility in the wave function. So it's just a half. But if photon 1 is transmitted, then that says that the polarization of 2 must also be along that in the same direction. So if we now submit that second photon to a polarizer set in direction B, then the probability of transmission is the cosine squared of the angle between A and B. That again is just the straightforward Malus's law. So what that means is that the probability that under these conditions both the photons get transmitted is a half times cosine squared theta AB. Next slide, please. Next slide, please. Again, okay. So just to recap, we have this these atoms which are excited into a high excited state and are cascading down to the ground state, emitting two photons back to back. And we're going to submit those two photons to polarizers, and behind the polarizer we'll put a detector. Sorry, there seem to be rather too many typos on this slide, on these slides, but anyway, it should read the probability that both photons are not deleted but detected. Probability of both detected, sorry, is a half cosine squared theta AB. We just saw that. The probability that neither is detected, well, it's the same line of argument. That gives you a half cosine squared theta AB again. The probability that one is detected but two is not is a half sine squared, the angle between them. And the probability of vice versa is again a half sine squared. These probabilities are different from what you'd get from just having a classical mixture of states which are either both polarized, say, in the x direction, or both polarized in the y direction, and so on and so forth. Anyway, these are the predictions of standard quantum mechanics. And what John Bell asked in his famous paper back in 1964 is, can these predictions be explained by a classical probabilistic theory? And he gave an answer to that question. Now, to understand the answer that Bell gave, we have to make a few definitions. Sorry, but this does make the argument a little easier if we do this. Suppose for a given pair, with polarizer 1 set in the A direction, photon 1 is detected. Then by definition, we say that there's a quantity capital A, which is plus 1. If the polarizer is set at A, again, but photon 1 is rejected, then A is minus 1. Similarly, with polarizer 2 set in the B direction, photon 2 is detected, we define capital B is plus 1, and if rejected, then B is minus 1. Then a concise statement of the formulae, which I've written in the green box higher up, is that for the average over the ensemble of pairs, the average of the product of A and B is the cosine squared of theta AB minus the sine squared of theta AB, and by simple trigonometry, that's just cosine twice theta AB. Remember, theta AB is the angle between the transmission directions of the two polarizers. Again, a mixture would be different. It would have a half in front, and that half actually turns out to be very crucial. But the quantum mechanical result is the cosine twice theta AB. Now, if we just look at two special cases of that, if the two polarizers are set exactly parallel, then the average of AB is just plus 1. That means that they're always exactly correlated. If theta AB is pi over 2, then the product AB is minus 1. And those two special cases, as it turns out, can actually be accounted for by a classical probabilistic model. Incidentally, it's amusing that these are the two special cases that, or at least they're strongly related to the two special cases that Einstein, Podolsky, and Rosen considered in their famous argument way back in 1935. But it turns out that in some sense they were wrong to draw special attention to those, because those two can be accounted for by a classical probabilistic model. However, something very, very interesting. Next slide, please. Next slide, please. Yeah. So again, this is to some extent a recap. We have an atomic source, atoms cascading down in the way we indicated earlier. But now we're going to pretty things up a little, because we're not going to always put photon 1 through a polarizer set in a particular direction. Rather, we're going to have a switch, which can switch that photon, number 1, into one of two different possibilities, one of which will measure, or will transmit photons polarized in the A direction, and the second will transmit photons polarized in the B direction. And similarly at the other end of the laboratory, with photon number 2 again can be switched into one of two polarizers. And again, we just make this definition to make the argument a little simpler. If photon 1 is switched into counter A and counter A clicks, then A is defined to be +1. If photon number 1 is switched into counter A and counter A does not click, then A is equal to -1. This is just definitions. But notice one thing. If photon 1 is actually switched not into counter A but into counter B, then the quantity A is for the moment at least simply not defined. Now, what can experiment measure? The experiment can measure the correlation of A and C on one set of pairs. That is, those pairs to which photon number 1 was switched by the random switch into counter A, and photon 2 was switched into counter C. You can measure the correlation of A and D on another set of pairs, those on which 1 was switched into A and 2 into D. Those are different sets of pairs. One quantity which turns out, for no obviously good reason at the moment, but it does turn out to be of special interest, is this quantity which I call K sub-experiment. And that, by definition, is the expectation, the average of A times C plus the average of A times D plus the average of B times C minus the average of B times D. That turns out to be a very special quantity, as we'll see. Okay, next slide, please. Now, okay, let's just step back for a moment and forget that we're doing quantum mechanics. We're just doing experiments and we're asking, as it were, what's going to come out. And so let's just define a class of theories about the physical world. Again, let me emphasize, this has nothing to do with quantum mechanics. We didn't know anything about quantum mechanics. We could just be doing these experiments for one reason or the other and just try to think about what we would expect. So let's make three postulates. One is local causality. That's a very fundamental postulate of special relativity. It means that events which are separated by a so-called space-like separation, that means there's no time for a light signal to travel between those two events, they cannot causally affect one another. Second principle is the normal arrow of time. That is, we assume that the past can affect the present and the present can affect the future, but not vice versa. And finally, we make this an assumption which could be formulated in either of two ways. One way, which was the way it was formulated in most of the older literature, is what we might call microscopic realism, which basically says that microscopic objects like photons have definite properties, whether or not we choose to measure those properties. So, for example, a photon has a polarization either along the x-axis, say, or along the y-axis, even if we don't choose to measure which it has. That turns out, in some sense, to be slightly uncomfortable when we try to put it together in some sense with quantum mechanics. So Henry Stapp and others proposed a different version of this principle, which we call macroscopic counterfactual definiteness. And basically what that says is that there is a definite result which I would have got if I had done a particular experiment. So in particular, in this case, suppose that that photon number 1 is actually switched into counter B. Well, I could have, well, counter B would either clicks or it doesn't click, and there's no particular mystery about that. But I could have switched that same photon into counter A. And then I make the postulate that either counter A would have clicked or it would not have clicked. In other words, it's a fact about the world, either that counter A would have clicked or that counter A would not have clicked. That's rather subtle, and I'll come back to that point later. Anyway, put these together. I'm going to go through this argument. Perhaps it would be a little fast, but all I want to call attention to really here is that each of these steps is extremely simple. You can almost say it's trivial. Each of the individual steps is so simple as to be trivial. But putting them together and get something rather interesting. So step 1 of the argument. Each photon number 1 by postulate number 3. What postulate number 3 is saying, when expressed in terms of the language I used earlier, is that either the variable A is +1 or it's -1, independently of whether or not A is actually measured. Next, postulate number 2, step number 2 is that by postulate number 1, local causality, the value of A for any particular photon 1 is unaffected by whether it was C or D we chose to measure on the corresponding photon 2, and vice versa, etc. Now, if you put this together, you can deduce the fact that for each pair of photons, 1 and 2, quantities AC, AD, BC, and BD each exist with AB, C, and D equal to ±1, and crucially, A the same in the combinations AC and AD, etc. Okay. After this, the next step is very trivial. For each, if 3 is true, then it's a matter of simple algebra to show that for each pair, the combination AC plus AD plus BC minus BD must be less than or equal to 2. If you doubt that, well, there are only 16 possibilities. So you can just exhaust them, and you find that's always true. Therefore, for a single ensemble, you find that the ensemble averages have the same property, that the ensemble average of AC plus that of AD, etc., is again less than or equal to 2. Now, the final step is not totally trivial, and this is the only point at which you need to invoke principle number 2. 2 is basically saying is that the ensemble of photons has properties independent of what you choose, as it were, at a later time to measure. Anyway, I think there's probably an important line falling off the bottom, but it will be reproduced on the next slide. So let's Next slide, please. Yeah. So, any objective local theory, that is, any theory which is defined by the conjunction of the three postulates I listed on the last slide, has to satisfy the result that the experimental value of k is less than or equal to 2. Well, so far so good. So what about that? Well, let's look at what quantum mechanics says. If in quantum mechanics, if the polarizer settings are A, B, C, and D, then, for example, for a 0+ transition of the atom, we predict, as we saw previously, we predict that AC is cosine of 2 theta A sub C. And if you arrange A, B, C, and D, that is the polarizer settings, so please stay on the last slide. No, please go back to the, yeah, good, thank you. If you arrange the polarizer settings in this particular way, then in the ideal case, quantum mechanics predicts that the experimental value of k is twice √2. And lo and behold, twice √2 is not less than or equal to 2. So what this means then is that the experimental predictions of quantum mechanics are incompatible with those of any theory of the world which embodies all these three principles: local causality, the arrow of time, and let us say macroscopic counterfactual definiteness. Now, that once it was realized how exciting this prediction was, people immediately started trying to do experiments to see which was actually right. Does the experiment satisfy the objective local theory inequality, that is, that k is less than or equal to 2, or does it satisfy the quantum mechanical result that k is, well, maybe not quite 2 √2, but certainly greater than 2? So please stay on the last slide for a moment. Yeah, thank you. And, well, by now there must have been, I don't know, hundreds of experiments done over the last 50 years. And just about all of them come out with the result that the quantum mechanical result is right. In other words, one of these three principles has to go. Well, that looks pretty serious. If we throw away local causality, the whole structure of Einstein's special relativity fails. And that, for most physicists at least, that would be a major disaster. I think popular writers on this subject seem not to mind this quite so much, but physicists really, really don't like the idea of throwing away local causality. If we throw away our normal ideas about the arrow of time, again, it's a major disaster because, after all, this principle is sort of built in to the construction and interpretation of just about every experiment we do. So again, most physicists don't like to throw that away. So what about the third principle, macroscopic counterfactual definiteness? Let me just remind you what that means, or what we're talking about. We suppose that a particular photon, number 1, say, was actually switched into counter B. And then, well, we know for sure that either counter B clicked or it didn't. Well, that's an experimental fact. Nothing mysterious about that. Now, suppose that we had in fact switched that photon number 1 into counter A. Then we can make two possible statements about what would have happened. But I don't think this distinction is a peculiarity of the English language. You might want to try translating it into Spanish and seeing if it still works. I think it probably does. So statement number 1 is that it's a fact about the world that either A would have clicked or A would not have clicked. Well, we know for sure that when we do switch the photon into counter A, one of those two things happen. So it looks as if that's pretty much a sort of tautology. Statement 2 is very subtly different. Either it is a fact about the world that I would have clicked, or it is a fact that I would not have clicked. That's not quite the same statement. And that is the statement which both physicists and philosophers nowadays tend to call counterfactual definiteness. Technically, in philosophical terms, the statement that counterfactual statements have truth values. I should just mention that counterfactual definiteness is something which we very, very definitely assume in ordinary life. I mean, if I say to you, had I got up 5 minutes earlier this morning, I would have caught the 8 o'clock bus. It doesn't occur to you to say, well, that's not a meaningful statement, right? Again, in the legal world, the prosecuting counsel can say to the jury, had the accused not pushed his victim down the stairs, she would be alive today. Again, that's a counterfactual statement. Again, the jury doesn't doubt that statement is meaningful. So certainly in everyday life, we do believe in macroscopic counterfactual definiteness. It looks as if perhaps at this level in physics, we can't. And I think that's a very, very profound statement about the world, which is due to Bell's original work. Okay, let's check how I'm going for time, I think. Yep, okay, I better try to speed up, I think, because I still have quite a lot I'd like to tell you. Okay, so Bell's theorem really started off a complete new field, quantum information, and a fundamental idea in quantum information is the idea of entanglement. Next slide, please. Yeah. Okay, suppose we have a system composed of two separated subsystems 1 and 2. Then, in general, the wave function, which in quantum mechanics describes these two systems, will be a function both of 1 and of 2. In the simplest case, it's just a product. It's just some wave function referring to 1 multiplied by some wave function referring to 2. In that case, we call it non-entangled. The properties of 1 are described exclusively by chi of 1, properties of 2 by phi of 2. And complete information on the system can be obtained by making measurements on the subsystems separately. That's not terribly interesting. Much more interesting is the case where psi is not a simple product. And that we already met it in the case of the two photons, so-called, sometimes called an EPR pair. We remember that in that case, the two photon wave function was of this form x1, x2 plus y1, y2. Now you can't factorize that into something which refers only to 1 and something which refers only to 2. They're intrinsically locked together. And under these conditions, it turns out that subsystems 1 and 2 don't in some sense possess individual properties in their own right. That basically is the content of Bell's theorem, although we've actually met in a slightly different language. And complete information about the system then can be obtained only by correlated measurements on 1 and 2. And that in turn means that the information stored in the system is non-local. And that's really in some sense the fundamental point about entanglement. Next slide, please. Let's just talk briefly about some applications where I probably won't get through everything I want to say about this, but let's start. First of all, suppose we have the following problem. Alice, labeled A in this diagram, is to transmit to Bob, who's up in the right-hand corner, an arbitrary state of a photon, which she may not even know herself. And she's to do that without direct physical contact. However, what she is allowed to do is either herself or via an agent to communicate with Bob by a classical phone line? Can she reliably transmit the unknown state of a photon? Answer yes. We'll just see in the next you've got how she does it. Next slide, please. Yeah. The solution is that C, we won't call Claire, emits a so-called EPR pair. That's a pair of photons with this funny property that we already saw. D, David, then measures the combined state of the red. So Claire emits the green and blue photons as an EPR pair. D then measures the combined state of the red photon, which is what Alice sent, and the green photon. If D finds an EPR pair, then it's a rather simple argument, which I won't try to go through, but it is straightforward. Angular momentum conservation then implies that the state received by B is exactly the one sent by A. And D, so all D needs to do is to pick up the phone, call B, and tell him he's found an EPR pair. If D finds a different state, then it turns out he can rotate it into an EPR pair. And he again tells Bob must perform the inverse of this rotation, and D instructs him so. So that's not perhaps particularly dramatic, but let's go on. Next slide, please. Next slide, please. Yeah. This is really something which is really by now quite practical, of quite practical interest. In classical cryptography, in some sense, the fundamental problem is how to distribute a key between how A and B are to distribute a key between them, or to say how A is to distribute a key to B. The key is a string of ones and zeros. And Bob will be able to use it to decode Alice's messages. Alice must be able to communicate the key to Bob safely, but moreover, she must be able to know if there's an eavesdropper. Eavesdropper, of course, is called Eve. And classically, there's no 100% secure way of ensuring this. In quantum mechanics, it turns out there is. And here is one possible solution. This is not actually the original solution of Bennett and Brassard in 1984. It's the Eckert solution a few years later, but it illustrates the principle better in some ways. We arrange that a source, S, emits a string of EPR pairs to A and B. Alice measures in the vertical horizontal basis, or she measures in the 135 basis in a random way. And B measures similarly, also at random. At the end of the sequence, Alice and Bob inform one another by a classical phone line which basis they've used for each measurement. They discard the ones for which they used different bases, and they compare notes on a subset of the rest. If they always agree, they can be sure there's no eavesdropping, and then use the rest for the key. Why? Why do they know that if they always agree, there could have been no eavesdropping? Next slide, please. Oh, so, sorry, no, sorry, go back, please. Yeah, right. So I have to stay with this one for a moment. Yeah. Why does the fact that they always agree imply that there's no eavesdropper? Well, there could be an eavesdropper on the classical phone line, but she won't learn anything useful. Can Eve listen in on the quantum phone line, or the quantum line from S to B? Well, if she does, there's a theorem which says she cannot receive a state of arbitrary polarization of a photon and transmit it without spoiling it. So this is the famous no cloning theorem of quantum mechanics. So if Eve does try to listen in and thereby try to acquire knowledge about the key, she'll automatically spoil the correlation between A and B, and they will be able to know that she's listening in. That was a very, very fundamental discovery in cryptography when Bennett and Brassard first made it in 1984. And now it's used in some quite practical cryptographic devices. You can actually buy nowadays little quantum cryptographic machines, as it were, which at least to a certain extent will use this principle. It's been used to, for example, to make a bank transfer in Vienna, to report election results in Geneva, and so on and so forth. So it really is pretty practical. Next slide, please. Yeah. The final example is perhaps a little more tricky to understand. Well, they're all tricky to understand, but they're all rather spectacular. So let me just try to describe this briefly. This is quantum computation. And the general principle goes something like this. Suppose we have, we're talking about particles of spin-off half. A single particle spin-off half in a pure state is parameterized by two independent variables, for example, corresponding to the angles theta and phi made by the spin with the z-x axis. However, a collection of n particles of spin-off half in a product state is parameterized similarly by two independent variables for each. So how many is that in total? Well, it's just 2n. However, the same collection of n particles in a generic entangled state requires for its parameterization 2 to the n variables. So let's just take the simplest example, which is non-trivial, which is n equals 3. If we have 3 different spins, then they can either all be up, or 1 and 2 can be up and 3 down, or 1 can be up and 2 and 3 down, etc., etc. It's easy to count them, and you see that there are 8 different states. That's 2 to the 3. And this, the expansion of one's available space grows enormously when n gets much larger than 3, say n equals 10 or whatever. So what that then permits, as first observed by Peter Shaw in 1994, is massively parallel computation. That is, you can actually sort of steer a state through this enormous jungle of possible available states, and in that way, it actually turns out that the factorization, I mean, I won't go into the details of this, they're really pretty technical. The factorization of an n-digit number, which for a classical computer is exponential in n, for a quantum computer which uses this principle, it's parallel. And again, that was an enormously important discovery, and is the basis of an enormous, well, essentially a huge business today. People are ardently trying to build practical quantum computers. Okay, next slide, please. Next slide, please.
Professor Legget, we're having some troubles with the internet. We're trying to fix them right now.
Yes, okay. Okay. Yeah, okay. So I'm going to have to really speed up, I guess, but the very simplest design for a quantum computer is to couple together usually a fairly large number of so-called two-state systems. Nowadays, these are usually called qubits, quantum bits, in such a way that we can reliably perform single qubit operations, which are non-entangling, and also two qubit operations, which often are entangling. Just as an example, a very simple example of an interaction which entangles two qubits is the Heisenberg interaction acting on two spins. The Heisenberg interaction, remember, is J sigma 1 dot sigma 2. That's the dot product of the two spins. If I start off with the state 1 up, 2 down, which is non-entangled, then the Heisenberg interaction after an appropriate time will give me the state on the right-hand side, which is entangled. And so you certainly need to be able to entangle 2 and more qubits. Principal requirements for a qubit are that, first of all, you have only 2 states. Secondly, you have easy initialization and readout, and you have to be able to prepare your qubits in a state that you know for sure. You have to be able to read them out in a final state that you know for sure. It has to be scalable, and above all, it has to be decoherence free. What does that mean? Well, suppose I do have a state like the one on the right-hand side up there, the entangled state. If it's the 2 qubits are completely isolated from the rest of the world, that's fine. It'll be able to stay that way for as long as I want it to. But in general, you can never isolate your systems from the rest of the world. The rest of the world is going to come in, and it turns out, again, this is not obvious, I really have to just tell you this, but it turns out that the effect of the rest of the world, the so-called environment, is basically to mess up the phase relation between the 2 parts of that expression. In other words, the I might wander off from being I, which is exponential I pi over 2. It might wander off to be, I don't know, a to the I pi over 6 or something of the kind. So in other words, it'll spoil the phase relation, and that phase relation is absolutely essential to quantum computing, so it'll totally spoil quantum computing. And for quite some years at the beginning of the game, say in the early 90s, this was thought out to be a major objection to the idea of building a quantum computer. But people got very, very good at beating it, and it turns out we have a figure of merit for the lack of decoherence, that is the decoherence-free property, which is the characteristic frequency of our T-state system times the so-called dephasing or decoherence time. And current designs require that to be greater than or equal to about 10 to the 4. And it turns out that there are a really remarkable number of systems, including some quite surprising ones, which do actually satisfy this condition. And I'm not going to have time because I think I really do have to stop in a minute or two, but I'll just show you very briefly a physical picture of one of the kinds of qubit which I'm particularly interested in. Next slide, please. Yeah, this is actually courtesy of my my experimental colleague Delbert Harlingen at the University of Illinois. And it's basically a device based on the Josephson effect, and you see the scale at the top, 0.35 millimeters, and the operative bit of it is the little, I'll describe it. I don't know if you can see the cursor, but it's this, it's the little bit of the 2/3 of the way up the lower diagram. And this is, this is actually built out of superconductors. And what's actually rather remarkable is that this qubit is not a microscopic object. People used to, when the whole idea of quantum computing was first floated, people used to think that you were going to need some very microscopic things like nuclear spins or trapped ions and so on to make a quantum computer. And indeed, you may be able to do this. But what's very interesting is that this kind of device, the technical name for this device is a flux qubit. And this is now one of the major candidates for building a quantum computer. So it's a macroscopic, you see the scale here, so it's, I don't know, about a fraction of a millimeter here. But you see it's actually macroscopic, and yet it is behaving according to the laws of quantum mechanics and could be an element in a quantum computer. For many, many years, people thought this was impossible. And when I and a few others started around 1980 to suggest that you could seriously see quantum effects in this kind of macroscopic system, we were pretty much laughed out of court. But nowadays, it's just everyday stuff. People just build these devices and do experiments on them every day. And sure enough, yes, They are macroscopic objects which do show real quantum mechanical effects. That would be a whole lecture in itself, which alas I don't have time for. So I'm just going to have to sign off at this point. But I would just re-emphasize the fact that this little paper of John Bell, 50 years, somewhat more than 50 years ago, which at first sight seems so abstract as to be of no practical use to anyone, is now the basis of a multi-billion dollar industry, the quantum computing industry. Thank you. Okay. End.
Thank you very much, Professor Legget, for your lecture. We will now move on to the question and answer session. For Zoom audience, you can send your questions by sending a direct message to the person named in Plexis Q&A. For the persons here at the Congress Center, you can begin with by raising your hands with the questions.
Okay. Well, thank you so much for the presentation. I think it is wonderful to see the EPR concept working in physics. And well, we mentioned a lot about the atoms dealing with light particles with photons. What is we talk about matter, and how is the concept of polarization over photons? How does it work over thermodynamical systems or even complex systems as a black body concept? How will it work?
I'm sorry, I'm not quite sure that I understood your question correctly. Are you asking what is the analog of polarization for other systems besides photons?
Yes, yes, exactly.
Okay. Well, for example, if I have a single atom or a single nucleus, it will have spin, or it may have spin, and the spin again can be oriented in different directions. And so, crudely speaking, I mean, it's not it's not a completely simple analog, but there is an analog between the direction of polarization of a photon and the direction of spin of an atom or a nucleus. And you can do much the same sort of thing with, say nuclear spins as you can with photons. If you're talking about something more complicated than that, like these so-called flux qubits, well, it turns out there is a variable which is similar to the photon polarization. It's more complicated. Really, it has to do with the currents flowing in this macroscopic object, in this macroscopic ring. Again, you have just as you have two possible polarizations, two possible directions, or if I have a nuclear spin a half, it has two possible orientations, up or down. Similarly, in the case of this flux qubit, where I showed you the picture of that, the two states in question are the current flowing clockwise or anti-clockwise around the loop. Now, what I think is less easy to visualize is what is the analog of changing the polarization axes in the case of a photon. In the case of the nuclear spins, well, you again can essentially change the direction of the axes. In the case of the flux qubit, it's a little more complicated. There is a variable. It turns out you don't measure the circulating current clockwise or clockwise. You measure something a bit more complicated, which I need quite a bit of time to explain. But you can essentially do the same thing. Sorry, I don't know if I answered your question.
Yes, thank you so much.
We have a question from our Zoom audience. Based on what we discussed, which quantum computer architecture do you think that is going to be the best one for implementing quantum algorithms?
Sorry, again, I have to ask you to repeat that. What is the something which is going to be best from the point of view of quantum algorithms?
Yeah, the question is, based on what we discussed, which quantum computer architecture do you think that is going to be the best one for implementing quantum algorithms?
Well, I think that almost certainly depends on what kind of quantum algorithm you want to implement. I mean, as you perhaps know, there are already certain devices built by the D-Wave company in Vancouver, which claim to be quantum computers. It's not clear that they are really what most people working in the field would call quantum computers. They're computers which do exploit quantum mechanical principles, but not the sort of quantum mechanical principles that I've been talking about, or at least not obviously so. Again, if you want to build, I should say these D-Wave quantum computers, as far as I know, are built for very special purposes. They're built to solve problems which are generally speaking the so-called traveling salesman type, where you have to exhaust a very large number of possibilities and figure out which is going to be the best one. Classically, this is a very, very hard problem, and it is believed that you can actually speed it up by applying quantum mechanics, but it's a very special problem, so you need a very special architecture for it. So I don't think your question, what is the best architecture for implementing quantum algorithms, really has a unique answer. As I say, it depends on what is the precise quantum algorithm you're trying to exploit.
Yeah, go. The microphone is up.
Okay, another question here regarding the quantum computers. We're on the qubit side. How does entanglement help or interfere with creating algorithms? Does it add an unnecessary complexity, or is it actually helpful in generating algorithms?
Yeah, well, it turns out in some sense, there are a whole crowd of algorithms that really unique to a quantum computer, because they rely on the possibility of being able to guide the system through any one, in some sense simultaneously, through any one of a large number of paths. That is something which really has no classical analog. It's this possibility of in some sense being able to explore many different paths simultaneously, while not, as it were, committing yourself to one of the paths, which is the intrinsic feature of quantum computing. Incidentally, there's an obvious difficulty which people raised at a very early stage in this whole game. And nowadays you still hear it raised sometimes as a sort of generic objection to the whole idea of quantum computing. People say, well, okay, you can create these states which are highly entangled, which are superpositions of huge numbers of different states. But if you actually make a measurement, you're actually only going to hit one of these states. Now, it's a basic principle of quantum mechanics that if I make a measurement, I get a single result. I don't get a whole slew of results. So don't you essentially waste all these different paths? And basically the answer was given by Peter Shaw and others. Basically what you do is to construct an algorithm which always ends up in a single state. But depending on the answer to your question, that state will be different. So at the end of the day, yes, you do always measure a single state, despite the fact that in the intermediate stages, you've gone through this enormous, technically this enormous Hilbert space in some sense, exploring millions and millions of different possibilities at the same time.
Okay, thank you very much, Professor. Is there another question?
Yes, Doctor, thank you very much for the talk. I was wondering if you have a reading material or a favorite book or anything for the audience to begin to understand this world of quantum computing.
Okay, yeah, there have been lots and lots of books at various levels written over the last 20 years or so on this subject, specifically with respect to, I mean, I should say there are a lot of books written about Bell's theorem and the EPR paradox and so forth, which were written before the advent of quantum computing, but are very good on the conceptual questions involved. The one I like rather well is by Nick Herbert, Herbert, called Quantum Reality. It's quite an old book, but by now I think sometime around 1980 or thereabouts. But it really is I think quite good, and it's written at a level which I think probably certainly can be understood by, say, a senior undergraduate student. Since the advent of quantum computing, again, there have been lots and lots. Again, it depends what level you want it. At the, say, at the layman or perhaps senior undergraduate level, there is a book by Gerard Milburn, Milburn, called The Feynman Processor. That's essentially a layman's introduction to quantum computing. If you want something more technical, if you're prepared to spend a certain amount of effort getting into it, then there is a very standard book by Nielsen and Chuang, which is, I think, by now probably 15, maybe even 20 years old, called Quantum Information and Quantum Computing. I think that's the right title. And that's, as I said, it's more a standard textbook. If you're going to become a specialist in that area, that's the sort of thing you start on. But the Milburn book is a much simpler level. Almost certainly there are many more books that I don't even know about because it's been a major industry over the last 15 years or so. But if you go to the library, the place to, I think the words to look under are quantum information or possibly quantum computing. Quantum information is a wider term than quantum computing, and it embraces quantum computing, but also quantum cryptography, teleportation, and so on and so forth.
Thank you, Professor, for your answer. We have just we just have time for one more question.
Professor, you mentioned that one of the problems with using qubits was making sure there was little decoherence. So how is that usually carried out?
I'm sorry, I'm afraid you have to repeat the question. I didn't hear it properly.
Sorry, my question is, how is decoherence avoided in quantum computers?
How is what avoided?
Decoherence?
Decoherence, yeah, okay, yeah, okay, thank you. The most obvious principle is that you just try to find a system which is very, very well isolated from the external world, except when you want to, as it were, address it. And a typical example of this would be nuclear spins. If you have the nuclear spins in some complicated molecule, say, then generally speaking, they're in very weak contact with the external world. But on the other hand, if you want to do something to them, what you do is to shine an intense beam of microwaves on them. Again, in the case of trapped ions, it's possible to make a little trap which will hold an ion in such a way that it's only very weakly affected by the external world. But then if you want to affect it, what you do is to shine a laser on it. The principle there is that we have a lasers and nature doesn't. So basically we can do things to the system while still preventing nature from doing anything to the system. So that's one principle. But a very interesting possibility has come up in the last 20 years or so, which is a bit different, which is the idea of so-called topological quantum computing. And the idea there is to bury the information, for example, the phase relation between the different states you want to use, to bury it in some complicated many-body state of a condensed matter system. By doing so, if you can find a complex enough state, or pair of states, really, or set of states, to bury your information in, what you can do is to ensure that, again, that nature doesn't really have much chance of spoiling it. But when you, when the experimenter sort of manages to how to put it, manages to engineer a particular kind of probe, a particular kind of sequence of pulses or something of the kind, that, as it were, unlocks the that state and manages to change it. So it's as if you had it's like a sort of lock in a way. An arbitrary person, and in this case nature, nature coming up to that lock, doesn't have the means to unlock it. You have a very special device, a key, which is just fitted to turn that lock. And so again, you can do something that nature can't there. And this is still, this whole idea of topological quantum computing is still at a pretty preliminary stage, but it's theoretically extremely interesting. And if it can be adequately implemented, it'll be extremely valuable.
Thank you very much, Professor Legget, for your participation on the International Symposium on Physics. We also like to take this opportunity to thank our sponsors, without whom this event would not be possible: Ternium, Climate AI, HV. Thank you very much for your presence, and see you tomorrow for Douglas Natelson's lecture, Noise and What It Can Tell Us About When Electrons Stop Acting Like Electrons, which will start at 10 a.m. And also I would like to remember you about the roundtable, which is tomorrow at 11:30 a.m. tomorrow.
Okay.
Thank you very much, Professor Legget.
Thank you for listening. Thank you.